Yes, I hope it works. Perfect. Thank you. And yes, do remind me if I do things like this. Let me just go to my collab. Regression. Can you see my slide? Sorry, my screen?
Yeah.
Perfect. The plot I'm talking about is any of those plots. You see, these are data and the red are predictions. So given this is a spread of temperatures, and this is the number of rides. So a given temperature, let's say 15 degrees, sometimes there were 10 rides, sometimes there were 400 rides with bikes and so on, right? And you see that there is a difference between the data and the prediction. In particular, since we are with you, Stefano, what do you think? What do you observe here?
I believe that maybe with the lasso regularization, maybe the spread will be lower.
So yeah, you see some differences, but even before regularization, remember that we are using a specific thing. We are doing linear regularization. We are allowing the cost function to be only a linear function of the inputs. So where does this model fail?
At higher temperatures.
Mm-hmm.
So maybe there is some kind of non-linear regime at higher temperatures?
It's possible, exactly. Clearly, this model, even though we started adding other features and it improved a bit, right, when we added the seasonality and so on, still it's not, I mean, it's really good. The error bar is small, but for example, it fails when it comes to high values of rides. So it doesn't predict high values. And as you were saying, Roberto, it also fails at high temperatures. So high values of the input too. So two things will be going on here. One of them is that we are limited by the linearity of our functional description. And the other is that we are not using enough variables as to take into account when this happens. What is behind this very high number of rides, or this very low number of rides when the temperature is high? Maybe there is another variable that we are not taking into account. Again, think that most of the density is over here, so the model is doing well, but it's obviously failing in some places. Okay? So when, for example, in the future, you can, for example, tomorrow, you might be able to do exactly the same stuff we've done. That is not yet machine learning. This is just linear regularization. Sorry, linear regression. And with a neural network, you might get better predictions. Or maybe you don't get better predictions. You get worse predictions just because the neural network wants a lot of good and new variables, and we are not giving it to them. So for that, I want you to pay attention to plotted for you the correlation matrix. What this is showing here, you can see it, right?
Yes.
Yes.
Thank you. Like, of course, each variable with itself is very correlated. This doesn't tell you anything. But there are things that are also highly correlated. Temperature and real field in temperature are highly correlated, and that's why you see this. I also plotted them or printed the numbers for you. There is one correlation, of course, between temperature and itself, real field and itself, but it's also these off-diagonal values are also high correlations between those. Why? Because temperature and real temperature, unless the wind speed is high, they are very, very much the same. So we see that here. Or for example, these lighter colors over here also tell us that humidity, weather, whether it's a good weather, bad weather, it's cloudy and whatever, are highly correlated too, no surprisingly. Or weather here, when we see over this corner over here, also in light color, it tells you that the total number of rentals and the ones that come from register are also very correlated, just because most users are users that have been registered already. So whenever you look at a multivariate problem, first thing you do is look at correlations. We've done a little bit, and this is really just the name of this feature engineering. It's just a fancy name to say that you should look at your variables and see whether some variables are useless, like here, temperature, real field. Maintaining those is useless, and in a neural network, it might confuse actually the network. And sometimes there are correlations that you want to take into account. For example, if this was extremely correlated, we will see very light colors everywhere. That will tell you that keeping all these variables is useless. And you actually need to, if you want to improve your precision, it's not by adding another yet very correlated feature that you are going to improve it. So yeah, we get good results, but not as good as you will get by trying to improve your model beyond linear, doing something more non-linear, but also trying to add more features if they exist. More things I wanted to tell you. So yeah, when you have a situation like this, regularization might not help you. Yeah, any questions I can hear?
Veronica,
Yeah.
can you hear me good?
Yes, I hear you very well.
I have a doubt with the correlation. Well, actually, is because of the procedure. Because you start watching that matrix, and after that, you pick just some features. So my point is, are you going to grab it? Are you going to pick some features because you knew it, or because you do any contrast like the statistics contrast with correlation of? Are you getting what I'm saying?
Yeah, well, let's see if I understand by answering what I think. So why do I look at this? For the moment, I'm just looking at the data, and I'm not doing any analysis yet. No. So here we are moving to the multivariate. There are many variables, and first thing I do always, you look at the data and see the correlations. And this is just also to show you some commands. Some of the things I wrote is just to make sure you know the commands, because you are going to use them later on. But you can also look at a smaller set of correlations just to see that this temperature and real field are very correlated, that the casual riders and total rentals are slightly correlated. So maybe there is a value of keeping this one. And then see what we do. I'm going to go down. You see that here you can look at the error bar you will get by having all these temperature, season, weather, humidity, or just dropping humidity, or just dropping weather. And you see, yeah, you see these numbers tells you that essentially the lower it is, the better you are doing. And these numbers tell you that, for example, adding humidity is important, whereas adding weather, it doesn't add that much, which we know because, let me go back here. You see humidity and weather are correlated.
Yeah.
Right?
Okay. Yeah.
So at the end, when people talk about feature engineering, it's just purposes in manipulating the data at the beginning, manipulating what you tell the machine to learn, so that it learns faster and more robustly. Because you will say, okay, but if my machine is my procedure is good, it doesn't matter that I give all these variables and they are all correlated. It would take all this into account and only extract the important parts of my features. The problem is that when you have noisy data, and when you have data that is not very large, like we had this discussion this morning about this polynomial of order 10. If you add data, even if it's very correlated, it might start trying to explain patterns that do not exist, in the sense that when you go to a higher set of data or a slightly different set of data, those patterns are not there. So there is a value of looking at your data, and if it makes sense to you, dropping features that you think are not interesting and they are not adding value, with always the idea that you are maybe going back to them when you have more data, and then you have the ability of maybe using those additional features only could bring a tiny bit more. Okay? More questions or comments or whatever.
Sorry, I have two questions. Can you hear me?
Yes, I hear you very well. A bit.
Okay. So the first question is about the subroutine train test RMSE. So
Yes.
I don't know if I understood well what it does. So I think for what I understood, I mean, I have some data set and for some features and the total rental, and then I divide this data set into parts, and I try to understand if I can predict well the X tests and Y tests. Is this what it does, or I understood wrong?
No, you understood right. So here you get your full data set of the variables for the bikes, so temperature and so on, and the total number of rentals. That's the X and the Y. And what you're going to do is to train on part of it, and once you have trained, you stop. You have your weights that you have obtained as the training set, and you're going to test on your test set whether you have good, you are going to okay. So in test split, I hope you can write in here. It takes your X, your Y, and automatically place them into a train, X test, Y train, and X. Already in the right amount. Meaning, for example, that your inputs, this essentially database with including for X and Y, and I'm going to take 90% of those countries
Sorry, Veronica, I don't hear you very well. I don't know if I'm the only one.
No, me also.
Neither. Yeah.
Me neither.
Same
really?
here.
I'm sorry. And let's see what I can do. So you don't hear me very well right now?
No, it's okay.
No, yes.
Okay, let me start over again. So this train test split is going to take your inputs and outputs, which are ordered, right? You have input corresponds to an output. So temperature, whatever, corresponds to number of rides, of a date, of an hour, and so on. And it's going to split them in let's say 80 or 90% train, and then 10 or 20% test. And that's what this command is doing. It's taking your X and Y and doing this for you. So this X train and Y train correspond to each other. X test and Y test correspond to each other. The random state 1 or whatever, this is simply because every time you do this train test splitting, it will do it in a completely different way, as it should, right? It's like you are shuffling your data. You go collect 80% of your data and train, 20% of the data, and you test. And if you do it again, you will be doing it with a different sample of data. But sometimes what people do is to write a random state number to be able to redo again and again and obtain exactly the same results. So instead of shuffling in a random way, it's always shuffling in exactly the same way. So you remove this, every time you run, it will be with a different amount, but different selection of test and train. Can you hear me now?
Yes, yes.
This was okay.
Yes.
So
And
this is a
whenever,
way to see, I mean, to test our predictions.
exactly. So you train
Okay.
and obtain the weights on only the train sample and use those weights to obtain predictions for your X test, right? So your
I am.
prediction for X test, I will give you a prediction, and then you can compare with the real value, which is Y test. And that is what we use to obtain, you see, these measures
Yes,
of
yes.
X.
Okay.
And, mhm. And in
I also,
general, yeah, go ahead.
yeah, sorry. No, no,
No,
I also had a second question, but it's not related to this. So continue,
no
please.
worries. Just wanted to say that whenever you see something like this and you wonder what it is, Google it because
Yeah,
there
yeah.
will there's explanations of it.
Okay, thanks.
I mean, you can ask me the question. Obviously, this is very important, and we are going to use it all the time. So it's great you ask. But just to say that if don't be shy, Google usually brings you to the best entry already. It's already
Yeah,
obtained.
yeah. I mean, I Googled that. It's just that I didn't understand why we were doing this. So, but now I understood.
It's important because that's exactly what we are going to be doing tomorrow as well in neural networks. So good. The other question?
Yes. So I'm not sure if I understood well what you were saying about our prediction, the plot with the prediction and the data. So for what I understood, you were saying that probably we don't have a best prediction because a good prediction because we are using a linear regression, and also because, I mean, for what I understood is because there might be other features involved. For example, for the high values of number of rides, that might not be the temperature, so we should take into account that we have some other variables that might explain this.
Exactly. And it
Okay.
might well be that there is you just don't have enough features variables. Even if you started digging deeper into how to improve your model, it could be that you just don't have access to these other reasons why sometimes the riding share is very large. I
Okay.
doubt it, right? We can always find reasons, but I guess what I wanted you guys to realize is that we've done the simplest, most stupidest thing, and we already get a good result, but this is improvable. And the way to improve it is to improve the way you look at the things, so your model, and also to add more features or more data. It looks like here the problem are features because there is plenty of data over here.
Thank you.
All right, more questions? I'm very glad that you came and you asked questions. That's great. Okay, so I'll see you tomorrow. We do neural networks. We'll start with real heavy load. Okay. See you tomorrow.